In this presentation, I'll be explaining the application of 555 timer as a monostable multivibrator. How can it be used as a monostable multivibrator? Coming to the monostable multivibrator using 555, this is the circuit diagram and this is the functional block diagram of 555. In this one circuit diagram, as you know that pin number 8 VCC, that is connected to VCC, 4 and 8 is shorted, and here it's the discharge pin, that is pin number 7, and this is the threshold pin number 6 and 7 are shorted, and to that one a resistance is connected from the VCC, that is the resistance, and capacitor is connected between the pin number 6 and ground. Therefore, this is externally connected value of the resistance, and capacitance is externally connected. That will be deciding the this time period. I shall be explaining that one. And here the trigger signal is connected to the pin number 2. Now, coming to the monostable circuit, let us see what is meant by monostable. Means that it is mono means one state is stable and other state is not stable, one quasi-stable state. Therefore, in monostable multivibrator, there is one stable state and there is one quasi-stable state. As we have seen here, this is assumed this is a triggering pulse like will be that is applied to the pin number 2. As that particular voltage is going less than say 1/3 VCC, the output is changing from low to high. The duration for which the output is low, that we defined as stable state. This is a stable state. Once the triggering pulse is going less than 1/3, the output is changing from the stable state into a quasi-stable state, because output is going high. That is a quasi-stable state, and the output is high for a certain duration that is defined by the capital T, that is declared as capital T, that is controlled by the product. The resistance and capacitance will be deciding this duration of the quasi-stable state. After that certain duration, output is going low, again coming back to the stable state. For this only, this is stable on this is a stable state and this is a quasi-stable state, and here the capacitor is charging from 0 to 2/3. During that duration you will be getting a high output, and that is the quasi-stable state. And after that, once the capacitor voltage is reaching to 2/3 VCC, output is going low and again coming back to the stable state. Therefore, this is the stable state. When output is low, we are taking it as a stable state. When output is high, it is called quasi-stable state. You can control the duration capital T by controlling the value of this resistance and capacitance that is externally connected. You can control the time period of T. Now, same circuit is shown here, the functional block diagram, in which here the two comparators, and this is a flip-flop, and this is the output, power amplifier input. It's an inverter actually, and there are two transistors. And here the externally you are connecting a resistance R, that is this resistance that is connected between VCC and the pin number. Pin number. Of course, here the 7 and 6 that is shorted. 7 and 6 are shorted. To that pin you are connecting the R, and then capacitor, that's pin number 7 and 6 are shorted to that R, and that from that shorted point you are connecting a capacitor like this capacitor between that point and the ground. Therefore, this is externally you are connecting R and C, you are externally connecting, and this is the triggering pulse that is given to the pin number 2, and this is the transistor which is connected internally. It is internal transistor, and actually that is coming across this capacitor. When transistor is on, here you can see that will be shorting this capacitor, and the capacitor voltage will become 0. Therefore, this is the internal block diagram, or that's called the functional block diagram of the 555 circuit, for that is connected for a monostable operation or monostable multivibrator operation. And in this case, to change from this is called quasi-stable state. To change from the quasi-stable state into the stable state to a stable state, no external triggering is required. In order to change from stable state to quasi-stable state, you have to apply a triggering signal, because you have to apply the voltage should be less than 1/3 VC. But once it comes to quasi-stable state, in order to return back from the quasi-stable state to the stable state, no external triggering is required in the case of a monostable multivibrator. Therefore, this is a monostable multivibrator using a 555 circuit. Now let us see the working of a monostable multivibrator circuit in using the 555 circuit. This is a functional block diagram which I already explained here. Externally, you are connecting a resistance R and capacitance is. This is the pin number 6 and pin number 7, number discharge pin, and this is the threshold pin. They are both are shorted, and triggering signal is applied to here. And initially, we are assuming that under steady state condition, the flip-flop holds the transistor Q1 on. For under steady state condition, we are assuming that output is low. That is, output is low here. Output is low. That is called stable state. And output is low here means this will become high, because this is an inverter. As this becomes high, the transistor is on. As this transistor is on means that capacitor voltage is shunted, or the capacitor voltage becomes 0. Therefore, initially the capacitor voltage is equal to 0 because the switch is on, the Q1 is on, that is coming across the capacitor, and the output equal to 0. And in steady state, control flip-flop holds the transistor Q1 on, connecting the external capacitor to the ground, and output remains at ground voltage. At the 0 voltage, output remains the ground voltage, the ground potential, which gives the low output. Therefore, you are getting a low output. Here you are getting a low output, that is called the stable state. Now, when a triggering pulse is applied at the pin number 2, when you are applying a triggering pulse which is going less than 1/3, as this voltage is going less than 1/3, because this voltage is already, it is equal to 1/3, because 3 resistors, they are divided. This is a 1/3 VCC. Now, as this voltage is going less than 1/3 VCC, here this will become going high, and therefore set pin will become going high. Set pin with going high means that here Q will become 1. Q will become 1 means Q bar will become low. QR is become low means that this transistor is getting turned off, and Q bar is here it is equal to Q bar equal to 0, or Q will become 1, Q bar equal to 0, transistor is getting turned off. Q equal to Q bar equal to 0 means that output will become high. Therefore, then output is going high. Output is going high, and the transistor is turned off. At that time, this capacitor is getting charged through the resistance R. Therefore, the capacitor is charging from 0 to towards, that is charging towards VCC. But once this capacitor voltage reaches to this 2/3 VCC, because this voltage is equal to 2/3 VCC. So once this crosses this 2/3 VCC, here this will become going high, or reset will become going high, or Q will become going low. Therefore, once this capacitor voltage reaches to 2/3 VCC, the Q will become high, Q will become low, or Q bar will become high, or Q bar will become high means that output become going low. Therefore, output is going low as this voltage reaching to 2/3. As output is going high or low means that this is going high. Q bar become high. As Q bar become high, the transistor is getting turned on, and the capacitor which is already charged by 2/3 VCC, that will be discharging suddenly through this, through the transistor, so that this is a discharging of the capacitor through the transistor, and the output voltage is changing to 0 voltage. Again, that is coming to the stable state. Therefore, this is the stable state, and this is the quasi-stable state. Therefore, this quasi-stable state duration is decided by the charging of the capacitor from 0 to 2/3 VCC. Therefore, when triggering pulse is applied, and as it passes through VCC by 3, as this passes to VCC by 3, the flip-flop is set. Therefore, this pin will become high, flip-flop will become set, and Q will become 1, and Q bar will become 0. Transistor Q1 gets turned off, that transistor is getting turned off, and output will be going high. That is, output is going high. Here output goes high, and the capacitor now gets charged, because output is going high means this is off, and the capacitor is getting charged from here to 2/3 VCC. Capacitor gets charged, and the voltage across it rises exponentially towards VCC. The capacitor voltage is increasing, and once the capacitor with the time constant RC, because capacitor is charging through this path with a time constant RC. After a time period capital T, after a time period of capital T, the capacitor voltage just crosses 2/3 VCC. That capacitor voltage is crossing, this capacitor voltage crosses 2/3 VCC, and as this crosses 2/3 VCC, this upper comparator becomes high and reset pin high, and here Q will become low. After time period T, capacitor voltage just crosses 2/3 VCC. Now the upper comparator output goes high, and the flip-flop Q will become 0 and Q bar will become 1. Q will become 0 and Q bar will become 1, meaning that this transistor is getting on, or the capacitor is suddenly discharging. At the same time, the output, since this is 1, output goes low, that is output is going low and capacitor is discharging. Continuing the monostable multivibrator working. Therefore, after the time period capital T, that is after this capital time period, that is that during that period it is in quasi-stable state. After that time period, after time period T, capacitor voltage just crosses 2/3 VCC. Therefore, the capacitor voltage is just crossing 2/3 VCC, means this voltage is just crossing 2/3 VCC, because here already 2/3 VCC is coming. Once this voltage is just crossing 2/3 VCC, this will become high, or reset pin will become high. As reset pin highs, here Q will become 0 or Q bar will become high. As Q bar become high, the transistor is getting turned on. As transistor is getting turned on, the capacitor gets discharged suddenly. That is what is happening. Capacitor is suddenly getting discharged. At the same time, the output is going low. That is, output is going low again to the stable state. Therefore, now the upper comparator output goes high and reset the flip-flops. Reset flip-flop, and Q will become 0 and Q bar will become 1. The transistor Q1 getting turned on. This again transistor getting turned on, thereby discharging the capacitor which is already in charge. That will be discharging through this transistor this rapidly, because this is directly connected to the ground. Capacitor suddenly discharging. That is why the discharging path is very quick, because it is, you are directly connecting the transistor which is on across the capacitor, that is suddenly discharging, and the output is changing to 0 voltage, rapidly to ground potential, and output is returning to the lower level. Lower level means 0 voltage, it is changing. Therefore, again that is changing to a stable state. Therefore, this is a stable state, or this is a stable state, and this is the quasi-stable state. And this duration, capital T, duration of the quasi-stable state, can be controlled by controlling the time constant, which is the product R and C. Therefore, that is the duration from the capacitor voltage is changing from 0 voltage to 2/3 VCC. Continuing the monostable multivibrator using 555, that is derivation of the quasi-stable state time period, because the quasi-stable state time period is this one, capital T. You have to calculate the equation, or you have to derive the equation for the capital T. And capital T means the capacitor voltage is changing from 0 voltage to 2/3 VCC. What is this duration? That is the capital T. And as you know that one, the capacitor voltage is at any instant can be, during the charging process, can be written as Vc equal to Vcc into 1 minus e raised to minus t by Rc. Or in this case, the time duration to change from 0 to 2/3 VCC, you have to substitute Vc equal to 2/3 VCC, and that duration is equal to capital T. Therefore, at time t equal to capital T, the capacitor voltage is changing to 2/3 VCC. Therefore, 2/3 VCC equal to Vcc into 1 minus e raised to minus t, capital T divided by Rc. Or from this equation, Vcc and Vcc get cancelled. Or 2/3 equal to 1 minus e raised to minus t by Rc. Or e raised to minus t by Rc equal to 1/3. Or e raised to t by Rc equal to 3. Or t equal to Rc natural logarithm of 3. It is equal to Rc natural logarithm of 3 equal to 1.1. Therefore, time period T, or the quasi-stable time period, that is this duration, capital T, is given by 1.1 times Rc. Therefore, the duration for which the capacitor voltage changes from 0 voltage to 2/3 VCC, that is called the quasi-stable state duration or period, that is equal to 1.1 times Rc, where R is the resistance and C is the capacitance, which they are connected externally. Now, in order to find out the value of the capacitance to be connected for a particular value of the time duration, for example, this graph will give for a time period of, say, I want to generate a time delay of 1 second. I want to generate that much. In order to generate a time delay of 1 second, corresponding to a resistance value of, say, 1 mega ohm, then I can get from this graph, this is the capacitance to be connected. Therefore, like that one, you can, from this graph, you can calculate for any time delay for a particular value of resistance, you can calculate what is the value of the capacitance to be selected. Therefore, the diagram depicts the relation between the resistance and capacitance for a required time delay. Therefore, in a monostable multivibrator, there is a one stable state and one quasi-stable state, and the duration of the quasi-stable state, capital T, that is equal to 1.1 Rc, that can be controlled by properly selecting the value of the resistance and capacitance which are connected externally. there is a problem in a monostable multivibrator using a 555 IC, and the resistance value is given as 100 kilo ohm, and the time delay required is given as 100 milliseconds. Therefore, this quasi-stable state duration is given as 100 milliseconds, and the resistance value that's to be connected externally is 100 kilo ohms. You are asked to find out what should be the value of the capacitance to be connected. Therefore, this is a monostable multivibrator circuit using the 555, in which you are externally connecting the resistance and capacitance that will be deciding the duration of the the quasi-stable state, which is given as 100 milliseconds. And the basic relation is given by, so as a solution, coming to the solution, capital T equal to 1.1 RC, where R value is given as 100 kilo ohm, and the total time capital T, that duration is given as 100 milliseconds. Therefore, substituting in this equation, you can find out, but this is the value of the capacitance required. Therefore, C is equal to, you'll be getting, it is equal to 0.9 microfarad. Therefore, if you connect a 0.9 microfarad as well as a 100 kilo ohm externally, then you can produce a delay of, say, 100 milliseconds. Therefore, by properly selecting the value of R and C, you can get any delay of this quasi-stable state, capital T, obeying this equation, capital T, or the time duration T equal to 1.1 RC. For monostable multivibrators can be used different application where you require, where you need a certain time delay. You can design the corresponding value of resistance and capacitance, and this is the stable state and this is the quasi-stable state, and the quasi-stable state duration equation is this one, T equal to 1.1 times RC. Therefore, this is a problem related to the monostable multivibrator using 555 IC.